Bismillah ar-Rahman Rahim. Assalamu alaikum. In the previous session, we have seen Cauchy's theorem. So, in this session, we will be moving forward to define Cauchy-Goursat theorem. So, recall in Cauchy's theorem, we had a function f of z, and we assume that it is analytic and it also analytic in domain D, and its derivative is also is continuous in D. So in other words, f was from C1 of D. So like C1 class, like it was continuous and its derivative was continuous. And of course, we had assumed that D is simply connected domain. Okay. So what basically Cauchy-Goursat theorem states. So in 1883, it was the French mathematician Idiot Goursat who proved that the assumption of continuity of differentiation can be removed. So he said that you can remove this assumption and still you can get the results whatever you have already seen in the Cauchy's theorem. So in Cauchy's theorem we have seen that for all of these assumptions are contour integral over any simple closed curve was zero. So Goursat says that you can remove this assumption and still get the same result of the Cauchy's theorem. So let's now state the theorem, that is Cauchy-Goursat theorem. Cauchy-Goursat theorem. Cauchy-Goursat theorem. So don't forget that in this discussion our domain is simply connected. For multiply connected we will have different version of this Cauchy-Goursat theorem. So I will specify that I am talking about Cauchy-Goursat theorem in particular for simply connected domain. So simply connected domain. So you have to keep this in head. And what is simply connected domain? So a simply connected domain is the one without any hole. So like a domain where there is no any hole over there. So let me state what does it say. System says the following. Suppose that a function f is analytic in simply connected domain D, then for every simple closed contour C in D, we have this integral of f of z is 0. So what is difference between the Cauchy's theorem and Cauchy-Goursat theorem is nothing but assumption. In Cauchy's theorem we also assume that f derivative is continuous in the domain, but in this Cauchy-Goursat theorem we don't assume that. So like we relax the assumption, right? So I won't get into the proof of this, but I will be talking about some of the nicer consequences of this theorem. The very interesting thing is we can restate this theorem in another way. Suppose now that let's now not talk about the domain, but like we have got a simple closed contour in a complex plane. So like we have forgotten about the domain now. We are just given with a simple closed contour C, such a way that f is analytic on this. And one of the interesting other thing is going to be that there is no any hole inside it. So if I don't have domain but I have got a simple closed contour such that there is no any hole inside it, so I can treat this simple closed contour as a kind of simply connected domain, and I can restate my Cauchy-Goursat theorem for the closed contour, where I will not need to use the terminology of the domain, but I will be explaining in the following way. So I can also state that So it is Cauchy-Goursat theorem, but restated. If f is analytic, if f is analytic at all points, at all points within and on, within and on a simple closed contour C, then I have the following. So I have what? I have the same result, that over this contour my function has integral 0. So it has, kind of made our life easier to explain our Cauchy-Goursat theorem only for the simple closed contour. So like we are saying basically that we have a function f of z which is analytic, analytic on a simple closed contour C, uh, analytic on and analytic within also, analytic within that same simple closed contour. So if we have this, then we can say that over that contour f has integral 0, right? So graphically, if I have a simple closed contour and I have got a f of z in such a way that this f of z is analytic on this contour as well as inside this contour, then over this simple closed contour my this integral is going to be 0. So now we have kind of simplified to in order to understand the Cauchy-Goursat theorem. What are going to be some of the consequences? We have got some of the very nice result that we can achieve out of it. For example, you already know that if I consider f of z to be e to the z, now this function is entire. In other words, it is analytic at every complex number. So it is differentiable everywhere. So now if I am given with any contour C, I can say that this integral has to be 0. Why? Because this function is entire and this function has to be continuous at it has to be analytic at every point in the complex plane. So in particular, you give me any contour, simple closed contour, I can say that this function is going to be analytic on that, within that. So I have this, so whenever you integrate e to the z over any simple closed contour, you will always, without evaluating, you will write that this integral is 0. And if we consider a polynomial function of complex value, p of z to be a sub n z power n plus a sub n minus 1 z power n minus 1 till a1 z plus a naught. So if we consider polynomial function, then we know that polynomial function is entire. That means differentiable at every point, you can say that. So it is analytic at every point, and hence you can also, without solving, you can consider you can say that the contour integral over any simple closed contour of the polynomial function is always 0. So for example, if you have a circle and you want to integrate over circle this z square dz, so you will say that it is 0, because this is polynomial function. So it is, it has to be analytic at every point, and in particular it is going to be analytic at any considered circle as well as within that circle. So like you can consider any kind of polynomials. Let's say you consider z cube plus z square minus 2z plus 1, and you integrate this over a closed simple contour, then you can say that this is 0, right? Thirdly, you also know that sine and cosine are also entire and are continuous and are analytic at every point. So for given any contour simple closed, sine has the integral 0, and over any given simple closed contour cos has the integral 0, right? So these are the consequences of this Cauchy-Goursat theorem that we have stated for the simply connected domain. Next, we will be moving towards multiply connected. In the coming sessions, we will discuss how can we use Cauchy-Goursat theorem, or how can we integrate a function over a domain which is multiply connected, right? Let's work out this example. So we want to find out the integral over a simple simple closed contour of the function 1 over z square, where the simple closed contour is given by this ellipse. So we can plot this and see that how does it look like, right? This is an ellipse having the major axis as vertical. So this one over here is an ellipse, right? So our task will be to see whether we are in the assumptions of the Cauchy-Goursat theorem, and for that we will see that whether the function is analytic on this uh, uh, simple closed contour as well as inside. So we will see now that our function is f of z, which is 1 over z square. So at its denominator vanishes at z equal to 0. So like at origin it is not analytic, other than that it is analytic. So in particular it is going to be analytic on this as well, right? In particular, I can say that my function is not analytic at this origin, but this origin has nothing to do with my ellipse which is lying over here. So in other words, this function is analytic everywhere except this origin. So if it is analytic everywhere, so in particular it is going to be analytic at this simple closed contour as well as within this simple closed contour, and you have to write down this argument and conclude that this integral must vanish. But here I can say one point. Instead of considering this simple closed contour, if someone considered this closed contour x square plus y square is equal to 1, so now this is going to be the circle centered at origin. In this case I can't conclude that this integral is 0. Why? Because my function is not going to be in the assumptions of analyticity within this circle. Okay, so I can't conclude this. Thank you. One bottom line: if you like my videos and if you like my content, do subscribe, like, share, and always leave feedback so that it helps me motivate to work more.